Okay, today we're going to find the center of mass of a cone, solid cone of uniform density. Now, it's actually easiest geometrically to do this with the cone this way. Whoop. So we're going to do it with the cone in this orientation. It's just makes the setup easier, the geometry of it. So that makes this H, this R. This is our Z-axis. We can leave the origin up there. That doesn't matter for the X and Y axis. That doesn't matter. It actually makes it easier if we put it down here too. So make that X, this Y. Not there, not there. Okay, so symmetry tells us that the center mass and the X and Y coordinates are going to be right at the origin because we have our cone symmetrically set up on the X, Y, Z. So the Z goes right down through the center. So left and right X, mass is evenly distributed. Forward and back, the Y, mass is evenly distributed. So those positions are going to be 0 and 0. It's the Z that matters. As the cone progresses up the Z axis, it becomes wider, so there's more mass, the higher up it goes. So it's only the Z that we need to find. And so 1 over the whole mass of everything, integral of Z dm. So we have to add up every little atom, right? So that's what this says. We got to add up every little piece of mass and its Z position. So we got to break up this into little dm's, but since we're adding up the Z's, we want to get this dm in terms of dz so that we can add up over the Z's. So here's what we do to do that. Let me make this a little bit smaller. We're going to slice this cone into little slices that have a height of dz. And they've got a radius here, what we'll call little r. And the mass of that thing, that is going to give us our little dm. So our little mass element is going to be thin slices, discs or circular slices of this cone. And that is the key step of this type of integration, finding center of mass, and what we're going to do in the future, finding rotational inertia, is you have to figure out how you're going to break the extended object up into tiny little objects that make the summation easier. So here, adding up all these little discs as they go up is a super easy thing to do. Every little disk has its center mass right on the Z-axis, so it's just another little point of mass on that Z-axis. We got to add them all up. So how do we relate? We now have to relate dm to dz. Well, the whole thing, whole mass over the whole volume, that's a constant value. It's got uniform density, so mass over volume is a fixed number. That's going to be equal to every little mass element and every little volume element. That ratio is constant for that uniform cone. All right, so we want to solve this for dm. So we get that dm is going to be equal to whole mass over whole volume times the little tiny volume. All right, but we got a dv. I need to get it in dz. We need it in z, not v, but z. So we got to continue our transformation. And do I got a little space over there? Yeah, so I can say that this is m over v. Now this volume of this thing right here, the volume of that disk, that dv is pi r squared, the area of that disk, times the height, dz. So I can make this pi r squared dz. Now volume of the cone, I'm going to put that in there now too. And we get, so we're going to have that dm is equal to whole mass over the volume. Volume of a cone is 1/3 pi, this is capital R squared because it's the whole cone, times h. That is, and then we got another pi. Then we got the little r squared and the dz. So that's our dm. We can see that, whoops, sorry. We can see that our pi is going to cancel out. And that's a third down there, not a half, 1/3. All right, so let's plug this in and integrate then. So we get that z, the average position is 1/m. So all the constants here come out. The only thing that varies in this term is r. R varies, little r. Everything else is a constant. So I can pull that all out. So that's it. The 3 goes on top. 3. There's an m. Divided by an r squared, capital R squared, divided by an h. So there we can see our m disappears, or reduces to 1. And then divide, whatever m, then integrate of z r squared dz. And we're going from 0 up to h. Okay, so we got another issue here. R squared and dz. That little r varies with z, so we need to put it in terms of z. Remember, when you're integrating with respect to a certain variable, anything that varies with that variable has to be in terms of that variable. So now we're going to do a little transformation there. Well, this cone has a continual angle, right? So this circle for this height is related to that circle and that height, and related to that circle and that height. They all have a constant ratio of base to height. So we know that r over h is a constant value. So that's going to be equal to little r over z. Because my little r is here, and I'm calling this height z. I'll label that. So now I can solve for r there, and I get that r equals capital R over h times z. But that's a z squared, right? So I got to square that when I put that in there. So we've got the average position along the z-axis of all the mass is 3 over capital R squared h integral of z, and then z r squared is going to be capital R squared over h squared z squared dz. And we're going from 0 to h. All right, not a big fan of the long lines of equal signs, but we're going to do it here to save space. All right, we've got some things that are going to simplify. Like that r squared is going to cancel that r squared. This h squared is coming out to make it h cubed. So we're going to get 3h cubed integral of 0 to h integral of, rather, z cubed dz from 0 to h. All right. Looks like we're good. That's a pretty easy integral to evaluate. So we get 3h cubed. That's z to the 4th over 4 from 0 to h. And when we do that, we get h to the 4th h. We get 3/4 h. And that is, in fact, our answer. It's 3/4. I measured it from the tip, right? So it's 3/4 from the tip or 1/4 from the base. So, right, this is 1/4 h, and this is 3/4 h. That's how we find the location of the center of mass of a cone. And once again, I want to reiterate, it's this transformation and the identification of the mass element that makes these things possible, that geometric analysis of the situation to make dm into something that is integrable. All right, thanks.